Neptune shouldn't exist the way it does. For decades, we thought we understood this distant blue world, a simple ice giant, orbiting peacefully at the edge of our solar system. Then, scientists looked closer. What they found challenges everything we believed about planetary formation, atmospheric physics, and what's actually possible this far from the Sun. The planet we see in textbooks isn't the planet that's really out there, and the discoveries being made right now are forcing us to rewrite the rules. Let me show you what Neptune has been hiding. When Voyager 2 flew past Neptune in August 1989, it captured images that would define our understanding of this world for generations. That deep, vibrant blue sphere became iconic. Posters, documentaries, science textbooks all featured Neptune as this stunning sapphire jewel of the outer solar system, distinctly different from its neighbor Uranus. There's just one problem with that image. It's not real. Well, it's real, but it's been dramatically enhanced. The color you've seen your entire life was artificially deepened to make Neptune's cloud features more visible for scientific study. The actual color of Neptune? It's much closer to the pale cyan of Uranus than anyone realized. This revelation came in late 2023 when researchers finally normalized the color data properly across different imaging systems. For over 30 years, we've been looking at an exaggerated version of Neptune. And if scientists got something that fundamental wrong for that long, what else have we missed? The answer is almost everything. Start with what Neptune is supposedly made of. We've called it an ice giant for decades. The term suggests a world dominated by water ice, methane ice, ammonia ice, frozen materials that accumulated far from the Sun, where temperatures plummet to unimaginable lows. Standard planetary models describe a relatively simple three-layer structure: a small rocky core, a thick icy mantle, and a hydrogen-helium atmosphere on top. In December 2025, scientists published research that demolished this comfortable picture. Using advanced hybrid modeling techniques, they discovered something shocking. Neptune might not be icy at all. The planet could just as easily be dominated by rock as by water-rich ices. The rock-to-water mass ratio might range anywhere from 0.20 to 1.78. Think about what that means. We've categorized Neptune as an ice giant, but it might actually be more rock than ice. The entire classification could be wrong. It's like calling something a lake when it's actually mostly mud. This uncertainty exists because we've never sent a probe into Neptune's interior. Everything we know comes from gravitational measurements and observations of the magnetic field, data that can support multiple completely different internal configurations. The gravitational field tells us how mass is distributed, but it can't tell us what that mass actually is. Rock and ice under extreme pressure can produce similar gravitational signatures while being fundamentally different materials. If Neptune is rock-dominated rather than ice-dominated, we need to rethink how it formed. Current models already struggle with Neptune's formation. They can't quite explain how it grew large enough, fast enough, to capture its atmosphere before the early solar system's gas dissipated. If the planet's composition is radically different from what we assumed, those models become even more problematic. The implications reach beyond Neptune itself. Neptune-mass planets are among the most common types of exoplanets we've discovered orbiting other stars. Understanding how our Neptune formed is critical to understanding planetary systems throughout the galaxy. If we've been wrong about our own ice giant, we might be wrong about thousands of distant worlds too. But Neptune's interior holds secrets stranger than just its composition. Deep within the planet, under pressures that would crush any material we know, something extraordinary happens. Methane molecules get squeezed so intensely that they break apart. Carbon atoms separate from hydrogen. And then those carbon atoms do what carbon does under extreme pressure. They crystallize into diamonds. This isn't speculation anymore. Scientists have recreated the process in laboratories. They subjected plastics, long chains of carbon and hydrogen, similar to what exists inside Neptune, to conditions mimicking the planet's interior. Nearly every carbon atom in the samples transformed into nanodiamonds, just a few nanometers wide. On Neptune, those diamonds would grow much larger. We're talking about diamonds millions of carats in weight. Some might be the size of buildings. These massive gemstones would be denser than the surrounding material, so they'd slowly sink deeper into the planet's interior, raining downward through layers of supersonic ice, a bizarre state of matter where oxygen atoms form a rigid crystalline structure while hydrogen ions flow through it like a liquid. Over thousands of years, this diamond rain might accumulate into a thick layer surrounding Neptune's core. The planet's interior could contain more diamond material than exists in Earth's entire crust. Mountains of diamonds, slowly precipitating through an ocean of exotic ice, all hidden beneath cloud tops, so cold they'd freeze you solid in seconds. This diamond rain serves a purpose beyond being spectacularly strange. When diamonds sink, they transport heat from the interior upward through convection. They also carry carbon deeper into the planet, potentially driving movements in those conductive ice layers. These movements might help generate Neptune's magnetic field, which brings us to another mystery entirely. Neptune's magnetic field doesn't make sense. On Earth, our magnetic field emerges from convection in the liquid iron outer core. The field aligns roughly with our rotation axis, with magnetic north relatively close to geographic north. Neptune's field does nothing of the sort. The field center is displaced by about 0.55 planetary radii, meaning the magnetic field center sits closer to Neptune's cloud tops than to the planet's actual center in some regions. The field is also tilted 46.9 degrees relative to Neptune's rotation axis. This creates one of the most bizarre magnetic configurations in the solar system. Here's what that means in practice. Neptune's auroras don't occur at the poles like Earth's northern and southern lights. Instead, they appear at mid-latitudes, roughly where South America would be if you mapped Earth's geography onto Neptune. The magnetic field wobbles dramatically as the planet rotates, creating a constantly shifting pattern that would seem utterly alien to anyone familiar with Earth's relatively stable magnetic environment. Scientists struggled to explain this configuration for years. Standard dynamo models, the theories describing how planetary magnetic fields generate, couldn't produce Neptune's lopsided, tilted field. The breakthrough came when researchers proposed that Neptune's magnetic field doesn't originate in a large convecting core like Earth's. Instead, it generates in thin shells of conducting material in the upper mantle. This model works, but it requires Neptune's interior to have a layered structure far more complex than the simple three-layer model we started with. Computer simulations suggest that under the extreme temperatures and pressures inside Neptune, water, methane, and ammonia naturally separate into distinct layers. It's like oil and water. They simply won't mix under these conditions. Hydrogen gets squeezed out of the methane and ammonia that dominate the deep interior, creating sharp boundaries between different material zones. These immiscible layers could explain both the strange magnetic field and why Neptune's field differs so dramatically from Earth's, Jupiter's, and Saturn's. It's an elegant solution to a decades-old puzzle, but it also means Neptune's interior is far more sophisticated and structured than anyone imagined. Supporting this complex internal structure is an exotic molecule that cannot form on Earth, aquodium. Under the extreme pressures inside Neptune, hydrogen and oxygen can bond in configurations impossible under normal conditions. These exotic molecules might fill those thin conducting shells, generating the magnetic field through mechanisms we're only beginning to understand. The magnetic field mystery connects to another unexpected discovery. In March 2025, the James Webb Space Telescope finally captured clear images of Neptune's auroras. Astronomers had been trying to confirm auroral activity since Voyager 2 flew past in 1989. But those early observations only showed hints. JWST settled the question definitively, but the auroral observations revealed something troubling. Neptune's atmosphere has cooled dramatically in recent decades. Global temperatures in the stratosphere dropped by roughly 8 degrees Celsius between 2003 and 2018. This was completely unexpected. Neptune experiences seasons like Earth does, but each season lasts over 40 Earth years because Neptune takes 165 years to orbit the Sun. Scientists expected temperatures to be slowly rising during Neptune's early southern summer, not falling. Then things got even stranger. Between 2018 and 2020, Neptune's south polar region warmed by roughly 11 degrees Celsius, completely reversing the global cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Several theories attempt to explain these temperature swings. Changes in atmospheric chemistry might alter how efficiently the atmosphere radiates heat into space. Random weather variability could create temporary hot or cold periods. Neptune might somehow respond to the Sun's 11-year activity cycle, even though the planet receives only about 0.1% of the sunlight Earth gets. That last possibility is particularly intriguing because it shouldn't work. Neptune is so distant that solar variations should barely register. Yet the atmosphere seems surprisingly responsive to solar changes. It's as if Neptune has an amplification mechanism we don't understand, making the planet's atmosphere far more sensitive to external influences than physics suggests it should be. These temperature mysteries connect to Neptune's most paradoxical feature, its weather. the planet experiences the strongest sustained winds in the solar system, reaching speeds up to 2,100 kilometers per hour. That's 9 times stronger than the strongest winds on Earth. These supersonic gales tear across cloud tops where temperatures hover around negative 218 degrees Celsius, one of the coldest places in the solar system. This shouldn't be possible. Weather requires energy. On Earth, our weather systems are powered by solar heating. Warm air rises, cold air sinks, and the temperature differences drive circulation patterns that create wind. Neptune receives so little solar energy that it should be meteorologically dead, or at least sluggish. Instead, Neptune's atmosphere is violently active. Storm systems emerge and evolve within hours. Giant vortices larger than Earth circle the planet in 16 to 18 hours. The only explanation that makes sense is that Neptune's weather is powered primarily by internal heat rather than sunlight. And Neptune does generate substantial internal heat. The planet radiates about 3 times more energy than it receives from the Sun. Temperatures at Neptune's center reach approximately 5,400 Kelvin, nearly as hot as the surface of the Sun. This internal heat flows outward, driving atmospheric circulation and powering those impossible winds. But this creates yet another puzzle. Where does that internal heat come from? Neptune formed billions of years ago. It should have radiated away most of its primordial heat by now, leaving it as cold internally as it is externally. Something must be generating heat inside the planet, or some mechanism is preventing that heat from escaping as quickly as it should. The diamond rain might be part of the answer. As diamonds crystallize and sink, they release gravitational potential energy that converts to heat. The separation of those immiscible interior layers could also generate heat through a process called differentiation. Or perhaps heat is trapped by those layered structures, insulated from escaping into space by the complex internal architecture. Whatever the mechanism, that internal heat makes Neptune far more active than it has any right to be. And that activity manifests in ways that continue to surprise us. The storms themselves behave unlike anything seen elsewhere in the solar system. Neptune's most famous storm, the Great Dark Spot discovered by Voyager 2 in 1989, had completely vanished by the time Hubble observed Neptune just 5 years later. These massive anticyclonic vortices appear, rage across the planet for a few years, then disappear without a trace. In 2018, Hubble spotted a new dark vortex in Neptune's northern hemisphere. Observations in 2019 showed it drifting southward toward the equator, where such storms are expected to dissipate. Scientists prepared to watch the storm's death. Then in August 2020, something unprecedented happened. The storm reversed course. It doubled back northward, defying every prediction about how Neptunian storms should behave. This was the first time scientists had observed a storm on any planet abruptly change direction like this. Then Hubble spotted something even stranger. A smaller dark spot appeared briefly near the larger storm, possibly a piece that broke off before disappearing entirely. Computer simulations had predicted that Neptunian storms might break apart and spawn smaller vortices, but no one had ever observed it happening. The fact that this process occurred during one of the few times we were watching closely, suggests it might be common. We've just never had the capability to monitor Neptune continuously enough to catch these events. The storms themselves form through a process we're only beginning to understand. Cloud activity increases in a region 2 to 3 years before a dark spot becomes visible. Something happens deep in the atmosphere, triggering enhanced convection that eventually manifests as a massive visible vortex. What triggers that initial activity remains unclear. These mysteries aren't confined to Neptune's atmosphere. The planet's ring system contains features that shouldn't exist according to everything we know about orbital mechanics. Neptune has 5 distinct ring arcs, concentrated segments within the Adam's ring, named Fraternité, Égalité 1 and 2, Liberté, and Courage. These arcs occupy narrow ranges of orbital longitude and have remained remarkably stable since their discovery in 1984. This stability is impossible. Differential orbital motion should cause these arcs to spread out and dissipate within just a few months. Particles closer to Neptune orbit faster than those farther out, so any concentrated arc should smear into a uniform ring almost immediately. Yet Neptune's arcs have persisted for over 40 years. The leading theory suggests gravitational resonance with Neptune's moon Galatea somehow maintains the arcs, but the mechanism remains unclear. Recent observations have made the mystery deeper. The arcs Courage and Liberté have faded away, while Fraternité and Égalité remain stable. Why would some arcs disappear while others persist? Neptune's rings themselves are made of extremely dark material, likely organic compounds processed by radiation over billions of years. The proportion of dust in these rings is unusually high, between 20 and 70%. Most planetary rings are dominated by larger particles with only trace amounts of dust. Neptune's dust-rich rings suggest either a unique formation process or ongoing destruction of larger particles into smaller fragments. Every observation of Neptune reveals more questions than answers. The planet that seemed straightforward, a cold, distant ice giant, turns out to be one of the most complex and mysterious worlds in our solar system. From its possibly rocky interior to its diamond rain, from its bizarre magnetic field to its impossible weather, from its reversing storms to its paradoxical ring arcs, Neptune defies explanation at every level, and we've barely scratched the surface. Neptune's largest moon, Triton, presents its own collection of impossibilities, a world that shouldn't be where it is, shouldn't be geologically active, yet somehow manages both. The mysteries compound with every measurement, every observation, every attempt to understand this distant world. But here's what makes all of this truly fascinating. Neptune isn't just weird for the sake of being weird. Every strange feature, every unexpected discovery points toward fundamental gaps in our understanding of how planets work. The answers to Neptune's mysteries will reshape our comprehension of planetary science itself. And those answers are starting to emerge in ways no one anticipated. Triton shouldn't exist where it does. Neptune's largest moon orbits backward, retrograde motion completely opposite to Neptune's rotation. Every other major moon in the solar system orbits in the same direction as its planet spins. Triton alone breaks this rule. The implications are staggering. Retrograde orbits don't form naturally during planetary formation. The material that coalesces into moons carries the angular momentum of the original protoplanetary disk, creating orbits that match the planet's rotation. Always, without exception, except Triton. The only explanation that makes sense is capture. Triton wasn't born around Neptune. It came from somewhere else, likely the Kuiper Belt, that distant realm of icy objects beyond Neptune's orbit. Somehow, billions of years ago, Triton wandered too close to Neptune. Gravitational interactions slowed it down just enough to trap it in orbit. This capture event would have been catastrophic. Any moons already orbiting Neptune would have been scattered or destroyed by Triton's arrival. The gravitational chaos would have reshaped the entire system. We're looking at the aftermath of a cosmic collision that fundamentally altered Neptune's satellite architecture. But here's what makes Triton truly bizarre. It's geologically active. Voyager 2 discovered this in 1989, spotting active geysers erupting from Triton's surface. Nitrogen geysers, shooting material 8 kilometers into the thin atmosphere before winds carried it hundreds of kilometers downrange. Triton's surface temperature measures negative 391 degrees Fahrenheit. It's one of the coldest objects we've ever measured in the solar system. At those temperatures, nitrogen freezes solid. Yet somehow, something generates enough heat to create active geology. The leading theory involves tidal heating. As Triton orbits Neptune, gravitational forces flex and squeeze the moon's interior, generating friction and heat. But the calculations don't quite work. Triton's orbit is nearly circular now, which should minimize tidal heating. The amount of geological activity we observe seems impossible given the orbital configuration, unless Triton's interior contains something unexpected, some heat source we haven't accounted for. Or perhaps the tidal heating was more intense in the past, and we're seeing the delayed effects. Thermal energy slowly working its way to the surface over millions of years. Triton's geology itself defies easy explanation. The surface displays cantaloupe terrain, strange dimpled landscapes unlike anything else in the solar system. These features might represent cryovolcanic activity, where water-ammonia mixtures erupt instead of molten rock. But the exact formation mechanism remains unclear. The moon's future is equally fascinating and tragic. Triton's retrograde orbit creates tidal interactions that gradually drain orbital energy. The moon is slowly spiraling inward toward Neptune. In 3.6 billion years, Triton will cross Neptune's Roche limit, the distance at which tidal forces overcome the moon's self-gravity. When that happens, Triton will either crash into Neptune's atmosphere or be torn apart by tidal forces. If it breaks apart, the debris will form a new ring system around Neptune, potentially rivaling or exceeding Saturn's magnificent rings. Future astronomers, billions of years from now, will observe a Neptune surrounded by spectacular rings made from the shattered remains of its largest moon. For now, Triton remains one of the most intriguing objects in the outer solar system, a captured Kuiper Belt object displaying active geology despite temperatures that should freeze all activity solid, a moon orbiting backward, slowly falling toward inevitable destruction. But Triton isn't Neptune's only moon. The system contains 14 known satellites, most of them small, irregular bodies likely captured from the Kuiper belt alongside Triton. These outer irregular moons orbit at extreme distances, some taking more than 25 years to complete a single orbit. One of these moons, Nereid, has the most eccentric orbit of any large moon in the solar system. Its distance from Neptune varies by a factor of 7 during each orbit, from 1.4 million kilometers at closest approach to 9.7 million kilometers at its farthest point. This extreme elliptical orbit suggests Nereid might have been perturbed by Triton's capture event, flung into its current strange trajectory by the gravitational chaos. The inner regular moons, Naiad, Thalassa, Despina, Galatea, Larissa, and Proteus, orbit close to Neptune within the ring system. These moons are small, dark, and irregularly shaped. They're likely remnants of the original satellite system that survived Triton's arrival. Or perhaps they formed from debris after the capture event destroyed the original moons. Proteus deserves special mention. It's the second largest Neptunian moon after Triton, yet it wasn't discovered until Voyager 2's flyby, despite being larger than Nereid, which had been known since 1949. The reason? Proteus orbits so close to Neptune and reflects so little light that it remained invisible to Earth-based telescopes until spacecraft arrived. Proteus itself shouldn't exist in its current form. At 420 kilometers in diameter, it's right at the threshold where self-gravity should pull an object into a spherical shape. Yet Proteus is distinctly non-spherical, covered in craters and angular features. It appears to be as large as a body can get while remaining irregularly shaped. Any bigger, and it would collapse into a sphere. The regular moons interact with Neptune's ring system in complex ways. Galatea appears to shepherd the ring arcs, using gravitational resonances to maintain their stability. But the exact mechanism remains unclear, especially given the selective fading of some arcs while others persist. These moons and rings tell a story of violence and chaos in Neptune's past. The current configuration didn't emerge from orderly planetary formation. It's the result of capture events, gravitational disruptions, and ongoing orbital evolution that continues to reshape the system today. What triggered Triton's capture? How did it lose enough energy to become bound to Neptune? These questions have no definitive answers. One possibility involves a binary system, two Kuiper belt objects orbiting each other. If this binary wandered close to Neptune, tidal forces could have separated the pair, with one object escaping, while the other lost enough energy to be captured. Another scenario involves a three-body interaction with another planet. Perhaps Triton encountered Neptune during an era when the outer solar system was still dynamically active, with planets migrating and crossing orbits. A close encounter at just the right moment could have resulted in capture. Regardless of the mechanism, the capture must have been spectacular. The newly captured Triton would have been in a highly elliptical orbit, swinging far from Neptune before plunging back close to the planet. Tidal forces would have been extreme during these close passages, generating immense heat in Triton's interior. The moon might have been partially molten during this phase, thoroughly resurfacing and erasing any record of its earlier history. Over millions of years, tidal interactions gradually circularized Triton's orbit, while simultaneously causing it to spiral inward. The orbital energy dissipated as heat, both in Triton's interior and in Neptune's atmosphere. This process continues today, though at a much slower rate, given the now circular orbit. The tidal heating history explains Triton's relatively young surface. Voyager 2 found few impact craters on Triton compared to other icy moons, suggesting the surface has been resurfaced within the last few million years. Geologically recent, the nitrogen geysers might be the last gasps of a once much more vigorous geological activity, powered by tidal heating. Triton's atmosphere adds another layer of mystery. Despite the extreme cold, the Moon maintains a thin nitrogen atmosphere with trace amounts of methane. Atmospheric pressure is only 14 microbars, 70,000 times thinner than Earth's atmosphere. Yet this tenuous envelope creates weather, clouds, and seasonal changes. As Triton orbits Neptune, different hemispheres experience sunlight and darkness over the course of Neptune's 165-year orbital period. This creates extreme seasonal effects. Nitrogen ice sublimates in sunlight and condenses in darkness, causing the atmospheric pressure to vary dramatically over decades. We've observed Triton during only a tiny fraction of its seasonal cycle, leaving most of its atmospheric behavior unknown. The Moon's surface composition includes nitrogen ice, methane ice, carbon monoxide ice, and water ice, along with complex organic compounds that give some regions a pinkish color. This chemistry responds to solar radiation and seasonal temperature changes in ways we're only beginning to understand. Some scientists have proposed that Triton's subsurface might harbor a liquid water ocean beneath the icy crust. Tidal heating, combined with antifreeze compounds like ammonia, could maintain liquid water even at Triton's extreme distance from the Sun. If such an ocean exists, it would make Triton one of the most intriguing astrobiology targets in the solar system, a potential habitat for life in one of the coldest, darkest corners of our planetary family. Testing this hypothesis requires a dedicated mission to Triton, something that hasn't happened yet despite numerous proposals. The Moon's retrograde orbit makes it challenging to reach. Spacecraft approaching Neptune must match this backward motion, requiring more fuel and more complex trajectory planning than missions to prograde orbiting moons. Yet the scientific payoff would be enormous. Understanding Triton means understanding Kuiper Belt objects, since Triton is essentially a captured Kuiper Belt dwarf planet. It's our closest large example of that distant population, preserved in orbit around Neptune, where we can study it in detail. Triton might also tell us about Neptune's formation and early evolution. The gravitational interactions during capture would have revealed information about Neptune's mass distribution and internal structure. Modeling the capture event requires understanding Neptune's properties at that time, which in turn constrains how the planet formed and evolved. The Moon's geological activity connects to Neptune's own mysteries. If tidal heating can drive geology on Triton despite the extreme cold, perhaps similar processes operate within Neptune itself, contributing to the planet's anomalous heat output. The relationship between Moon and planet might be more complex than simple gravitational interaction. Every aspect of Triton challenges our expectations. A moon orbiting backward, active geology at temperatures that should freeze everything solid, a tenuous atmosphere that somehow persists despite constant loss to space, a captured body that survived the violence of its own capture to become Neptune's dominant satellite. The story of Triton is ultimately the story of Neptune itself, a system that refuses to behave as predicted, that generates mysteries faster than we can solve them, that reveals the universe to be stranger and more complex than our theories suggest. Understanding one requires understanding the other, and both remain tantalizingly just beyond our complete comprehension. The mysteries don't end with Triton. Neptune's ring system presents puzzles that fundamentally challenge our understanding of orbital dynamics. Most planetary rings form complete circles. Saturn's rings, Uranus's rings, Jupiter's faint gossamer rings. They all follow a basic principle. Material orbiting a planet spreads out evenly over time, creating uniform structures governed by simple gravitational mechanics. Neptune's rings refuse to cooperate. The Adam's ring, Neptune's outermost ring, contains 5 distinct arcs with peculiar French revolutionary names: Fraternité, Égalité 1 and 2, Liberté, and Courage. These arcs occupy only specific sections of the ring's orbit, concentrated in narrow ranges of longitude, while the rest of the ring remains nearly empty. This shouldn't be possible. Differential orbital motion, the fact that inner material orbits faster than outer material, should smear these arcs into complete rings within months. Every calculation says they should have dispersed decades ago. Yet they persist, stable and distinct, having changed only slightly since their initial detection in 1980. The explanation involves Galatea, a small inner moon that acts as a shepherd, using resonant gravitational interactions to confine the arc material. The mathematics works, technically, but barely. The system operates on a knife edge between stability and chaos. Remove Galatea, and the arcs would vanish. Alter the resonance slightly, and the structure collapses. Recent observations have complicated the picture further. The leading arcs, Courage and Liberté, have faded significantly or disappeared entirely. The trailing arcs, Fraternité and Égalité, remain persistent and stable. This selective disappearance wasn't predicted by any model. Why would some arcs vanish while others endure under identical physical conditions? The ring material itself adds another layer of mystery. Neptune's rings are composed of extremely dark material, likely organic compounds that have been processed by radiation over millions of years. The proportion of dust ranges between 20 and 70%, unusually high compared to Saturn's ice-dominated rings. This dusty composition makes the rings incredibly difficult to observe from Earth, requiring long exposures and careful image processing to detect at all. The optical depth of the rings remains low, meaning they contain relatively little material despite their vast extent. Where did this material come from? Was it captured from passing comets, debris from destroyed moons, material left over from Neptune's formation? Each possibility has problems. Captured material should have different compositions across the ring system. Destroyed moons should have created more debris. Primordial material should have been swept away or accreted long ago. The ring's darkness suggests something else entirely. Perhaps a chemical evolution we don't yet understand, where radiation and charged particles gradually transform simple ices into complex organic compounds. This process might be ongoing, continuously darkening the ring material over astronomical timescales. Voyager 2's brief encounter in 1989 captured our only close-up images of Neptune's rings. Those images revealed structure and detail impossible to see from Earth, but they also raise questions that remain unanswered 35 years later. The spacecraft's trajectory allowed only a snapshot, one moment in time for a dynamic system that evolves over decades and centuries. What we need is time, continuous monitoring, observations across multiple Neptunian seasons to watch how the rings change, how the arcs evolve, whether new structures form or existing ones disappear. From Earth, even with our most powerful telescopes, Neptune's rings appear as faint smudges, requiring hours of integration time to detect. The discovery of Neptune itself stands as one of astronomy's greatest intellectual achievements. Unlike every other planet, Neptune was found through mathematics before it was seen through telescopes. In the early 1800s, astronomers noticed something odd about Uranus. The planet wasn't where it should be. Its orbit deviated slightly from predictions based on Newtonian mechanics and the gravitational influence of the known planets. These deviations were small but persistent, and they suggested the presence of an eighth planet beyond Uranus, tugging on it with invisible gravitational force. Alexis Bouvard documented these irregularities, but died before solving the puzzle. Two mathematicians, John Couch Adams in England and Urbain Le Verrier in France, independently calculated where this hypothetical planet should be located based solely on Uranus's orbital perturbations. Le Verrier's calculations proved more influential. He sent his predictions to Johann Gottfried Galle at the Berlin Observatory, and on September 23, 1846, Galle pointed his telescope to the predicted location. Neptune appeared within 1 degree of Le Verrier's calculated position. This represented a stunning validation of Newtonian mechanics and mathematical astronomy. A planet had been discovered not through systematic sky surveys or accidental observation, but through pure theoretical calculation. The universe, it seemed, could be understood through equations. Gravity operated predictably across billions of kilometers. Mathematics revealed reality. Yet Neptune itself immediately began complicating this elegant picture. The planet's mass turned out to be different than predicted, about 17 Earth masses rather than the 30+ predicted by Le Verrier's calculations. The mathematical prediction had worked despite being based on partially incorrect assumptions. Lucky coincidence, or something deeper? Even today, Neptune's discovery raises philosophical questions about scientific prediction and the nature of scientific success. The calculations were wrong in detail, but right in principle. Does this represent the power of mathematical modeling or its limitations? Neptune's atmospheric behavior continues generating surprises. Between 2003 and 2018, collective datasets showed a decline in the planet's thermal brightness, indicating that globally average stratospheric temperatures dropped by roughly 8 degrees Celsius. This was completely unexpected. Neptune experiences seasons like Earth, but each season lasts over 40 Earth years, due to the planet's 165-year orbital period. Scientists expected temperatures to be slowly growing warmer during early southern summer, following the increasing solar heating as that hemisphere tilted toward the sun. Instead, temperatures fell dramatically. Then, in 2018, something even stranger happened. Observations from Gemini North and the Subaru telescope revealed that Neptune's polar stratosphere warmed by roughly 11 degrees Celsius between 2018 and 2020, completely reversing the previous cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Several theories attempt to explain these temperature swings, changes in atmospheric chemistry that alter cooling efficiency, random weather pattern variability, or responses to the 11-year solar activity cycle. The solar connection is particularly intriguing because Neptune receives only about 0.1% of the sunlight that Earth receives, yet its atmosphere appears surprisingly responsive to solar variations. How can a planet so distant from the Sun, receiving such minimal solar energy, show measurable atmospheric responses to solar cycles? What mechanism could amplify such weak forcing into the dramatic temperature changes we've observed? The thermosphere presents an even greater mystery. For reasons that remain obscure, this upper atmospheric layer maintains temperatures around 750 Kelvin, hot enough to melt lead. Neptune is too far from the Sun for ultraviolet radiation to generate this heat. Something else must be warming the thermosphere to such extreme temperatures. Candidates include atmospheric interaction with ions in Neptune's magnetic field, creating friction and heating similar to auroral processes on Earth. Gravity waves from the interior might dissipate in the upper atmosphere, converting mechanical energy into heat. Chemical reactions involving unexpected compounds could release energy. None of these explanations fully accounts for the observed temperatures. The planet's internal heat generation compounds the puzzle. Neptune emits about 3 times as much energy as it receives from the Sun. This excess energy must come from the interior, but the mechanism remains uncertain. Core cooling, gravitational contraction, chemical reactions in the deep interior, radioactive decay, each process contributes something, but the exact proportions and their interactions remain unclear. Temperatures at Neptune's center reach approximately 5,400 Kelvin, hot enough to glow if you could somehow see through the overlying layers. This internal heat drives the planet's dynamic weather, powering winds that reach 2,100 kilometers per hour, the strongest sustained winds of any planet in the solar system. How can a planet so cold at its cloud tops maintain such powerful atmospheric circulation? How does internal heat propagate through thousands of kilometers of dense material to reach the atmosphere and drive such violent weather? The energy transport mechanisms remain poorly understood. In March 2025, the James Webb Space Telescope finally captured Neptune's aurorae in detail, ending decades of speculation since Voyager 2 caught only tantalizing hints. The observations revealed something unexpected. The Neptunian atmosphere has cooled by hundreds of degrees in recent decades, making the aurora fainter than anticipated. But it's the location of these aurorae that truly defies expectation. Neptune's magnetic field is tilted 47 degrees away from its rotation axis, which means aurorae occur roughly over regions equivalent to where South America would be on Earth, rather than at the poles. Unlike Earth's polar light shows, Neptune's aurorae appear at mid-latitudes, creating an alien spectacle that hypothetical observers would witness without traveling to extreme latitudes. The magnetic field itself remains one of Neptune's most profound mysteries. The field's center is displaced by about 0.55 planetary radii from Neptune's geometric center and tilted 46.9 degrees relative to the rotational axis. This dramatic offset means the magnetic field center is actually closer to Neptune's cloud tops than to its planetary core in some regions. Both Uranus and Neptune share this bizarre magnetic configuration. Highly tilted fields significantly offset from the planet's centers. This similarity suggests a common mechanism, something fundamental about ice giant interiors that generates magnetic fields differently than terrestrial planets or gas giants. Recent research points toward an exotic molecule called aquadium, a substance that cannot be formed under Earth conditions. Computer simulations show that under the extreme temperatures and pressures inside Neptune, water, methane, and ammonia would naturally separate into immiscible layers like oil and water. Hydrogen would be squeezed out of the methane and ammonia that comprise much of the deep interior, creating distinct chemical zones. These layered, stratified regions could generate magnetic fields in thin shells of conducting material in the upper mantle, rather than through coherent convection in a large liquid core like Earth's dynamo. This would create a complex, multipolar field that wobbles dramatically as the planet rotates. Exactly what we observe. This oil and water-like interior structure could explain many of Neptune's peculiar properties: the magnetic field, the heat flow, the atmospheric dynamics, perhaps even the planet's surprising responsiveness to solar variations despite its extreme distance from the Sun. But it also raises new questions. How stable are these immiscible layers? Do they mix over geological timescales? Could convective processes occasionally breach the boundaries between layers, creating episodic changes in Neptune's magnetic field or heat output? We've observed Neptune for less than 2 centuries, a blink compared to the billions of years of its existence. Neptune's interior composition itself has recently been called into question by groundbreaking research from December 2025. Scientists now propose that Neptune may not be the icy world long imagined. New hybrid modeling reveals the planet could just as easily be dominated by rock as by water-rich ices, with rock-to-water mass ratios potentially ranging between 0.20 and 1.78. This discovery fundamentally challenges Neptune's classification as an ice giant. If the planet is more rock-dominated than ice-dominated, it would require completely rethinking how these distant worlds formed and evolved over billions of years. The uncertainty stems from never having sent a probe deep into Neptune's interior. Current models based on gravitational data and magnetic field observations can support multiple internal configurations: ice-dominated, rock-dominated, or something in between. Every measurement we have of Neptune is consistent with radically different interior structures. We've been building theories on ambiguous data, assuming ice giant composition because it seemed reasonable, not because we had definitive proof. The implications are staggering. Everything we thought we knew about Neptune's formation might need revision. If Neptune contains more rock than ice, it couldn't have formed where it currently resides. The outer solar system 4 billion years ago simply didn't contain enough rocky material at Neptune's distance to build a rock-dominated planet. This would mean Neptune formed much closer to the Sun, perhaps where Mars orbits today, and migrated outward through gravitational interactions with other planets. The nice model of solar system evolution already suggests the giant planets migrated from their birth positions, but a rock-dominated Neptune would require far more dramatic migration than previously imagined. But Neptune's mysteries extend far beyond its hidden interior. The planet's atmosphere presents puzzles that have confounded scientists for decades. Between 2003 and 2018, collective datasets showed Neptune's thermal brightness declining steadily, indicating globally average stratospheric temperatures dropped by roughly 8 degrees Celsius. This was completely unexpected. Neptune was entering early southern summer during this period. Scientists anticipated temperatures would slowly increase as that hemisphere received more sunlight, not plummet. Then something even stranger happened. Observations from Gemini North in 2019 and the Subaru telescope in 2020 revealed Neptune's south pole had warmed by roughly 11 degrees Celsius between 2018 and 2020. In just 2 years, the polar region reversed the previous 15-year cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Neptune experiences seasons like Earth, but each season lasts over 40 Earth years due to its 165-year orbital period. These aren't subtle seasonal variations. They're dramatic temperature swings across a world that receives only 1/10% of the sunlight Earth receives. How can Neptune's atmosphere respond so dramatically to such minimal solar input? Scientists have proposed multiple theories. Changes in atmospheric chemistry altering how effectively the atmosphere radiates heat, random weather pattern variability, or responses to the 11-year solar activity cycle, but none fully explain the observations. The solar connection is particularly perplexing. Neptune orbits 30 times farther from the Sun than Earth. At that distance, solar radiation should be negligible. Yet Neptune's stratosphere appears surprisingly responsive to solar variations. During solar maximum, when the Sun's output increases slightly, Neptune's upper atmosphere brightens. During solar minimum, it dims. The mechanism connecting such weak solar variations to atmospheric changes on this distant world remains one of planetary science's most intriguing puzzles. Neptune's internal heat adds another dimension to this mystery. The planet emits about 3 times as much energy as it receives from the Sun. This isn't reflected sunlight. It's heat flowing outward from Neptune's interior. Temperatures at Neptune's core reach approximately 5,400 Kelvin, hotter than the surface of the Sun. This internal furnace drives the planet's weather systems, powering storms and winds despite the minimal solar energy available. And what weather it creates. Neptune possesses the strongest sustained winds in the solar system, speeds reaching 2,100 kilometers per hour, nearly twice the speed of sound on Earth. These supersonic winds roar through an atmosphere where cloud-top temperatures approach 55 Kelvin, making Neptune's outer atmosphere one of the coldest places in the solar system. The paradox is profound. The coldest planetary atmosphere generating the fastest winds. The source of this atmospheric energy remains debated. Neptune's internal heat certainly contributes, but converting that heat into organized atmospheric motion at such extreme speeds requires mechanisms we don't fully understand. The planet's rapid rotation, a day lasts only 16 hours, creates powerful Coriolis forces. The thin atmospheric pressure allows winds to accelerate without the friction that limits terrestrial wind speeds. But these factors alone don't explain Neptune's extreme weather. Then there are the storms themselves. Dark spots appear and disappear on Neptune with bewildering unpredictability. These massive anticyclonic vortices, similar to Jupiter's Great Red Spot, behave unlike storms anywhere else. Astronomers using the Hubble Space Telescope watched one dark vortex discovered in 2018 begin drifting southward toward Neptune's equator, where such storms typically dissipate. But in August 2020, the vortex suddenly reversed course, doubling back northward. This represented the first time scientists had observed a Neptunian storm change direction. Computer simulations predicted such reversals were possible, but nobody had witnessed one. Then Hubble spotted another smaller dark spot in January that temporarily appeared near the larger vortex. Scientists speculated it might be a piece that broke off, drifted away, and disappeared, a process predicted by models but never observed. Dark spots on Neptune differ dramatically from Jupiter's long-lived storms. The Great Dark Spot discovered by Voyager 2 in 1989 had completely vanished by the time Hubble observed Neptune in 1994. These storms typically last only a few years. Their origins are preceded by increased cloud activity in a given region 2 to 3 years before the dark spot becomes visible. Their disappearance has been linked to companion clouds reaching the storm's center and blocking the blue wavelengths used to track the vortex. What drives these ephemeral storms? Why do they form, migrate, reverse course, and vanish so quickly compared to Jupiter's centuries-old storms? The answer probably involves Neptune's internal heat flow, its rapid rotation, and complex interactions between atmospheric layers. But the details remain frustratingly elusive. Neptune's thermosphere presents yet another atmospheric enigma. This outermost atmospheric layer maintains temperatures around 750 Kelvin, far hotter than would be expected for a world so distant from the Sun. Neptune is too far for ultraviolet radiation to generate such heat. One candidate heating mechanism involves atmospheric interactions with ions in Neptune's bizarre magnetic field. Another suggests gravity waves from the interior dissipate in the thermosphere, converting mechanical energy to heat. But neither explanation is proven. The planet's rings add another layer of mystery. Neptune possesses 5 main rings: Gal, Leverrier, Lassell, Arago, and Adams, along with several fainter dusty sheets. The Adams ring contains 5 distinct arcs named Fraternité, Égalité, 1 and 2, Liberté, and Courage. These arcs occupy narrow ranges of orbital longitude and have remained remarkably stable since their initial detection in 1980. They shouldn't exist. According to orbital mechanics, differential Keplerian motion should cause these arcs to spread out and dissipate within months. Each particle in the arc orbits at a slightly different speed based on its distance from Neptune. Over time, faster-moving inner particles should overtake slower outer particles, causing the arc to smear into a uniform ring. Yet these arcs have persisted for decades. Their stability probably relates to resonant interactions with Galatea, Neptune's inner shepherd moon. Galatea's gravity creates regions where particles can accumulate and remain confined, but the mathematics don't perfectly predict the observed arc positions and stability. Recent observations add another puzzle. The leading arcs, Courage and Liberté, have faded away, while the trailing arcs, Fraternité and Égalité, remain persistent and stable. Why would some arcs disappear while others endure? Neptune's rings consist of extremely dark material, likely organic compounds processed by radiation, similar to material in Uranus's rings. The proportion of dust in Neptune's rings ranges between 20 and 70%, unusually high compared to Saturn's icy rings. Their optical depth is low to moderate, never exceeding 0.1, making them difficult to observe even with powerful telescopes. These rings are ghosts, barely visible whispers of material orbiting a world at the edge of the solar system. But perhaps Neptune's greatest mystery orbits the planet rather than comprising it. Triton, Neptune's largest moon, is one of the strangest objects in the solar system. It's the only large moon that orbits its planet in a retrograde direction, revolving opposite to Neptune's rotation. This backward orbit proves Triton wasn't born alongside Neptune. It was captured, probably from the Kuiper Belt, where it once wandered as an independent dwarf planet. That capture event would have been catastrophic. Triton's arrival would have scattered or destroyed any moons that orbited Neptune previously. Gravitational interactions during capture would have left Triton in a highly elliptical orbit initially. Tidal forces would have circularized that orbit over millions of years, generating enormous heat in Triton's interior through tidal flexing. Even today, billions of years after capture, Triton displays remarkable geological activity despite surface temperatures of negative 235 degrees Celsius, making it one of the coldest objects ever measured in the solar system. Voyager 2 discovered active geysers on Triton during its 1989 flyby. These nitrogen geysers erupt through Triton's icy crust, creating dark plumes that rise 8 kilometers above the surface before being swept downwind by Triton's thin atmosphere. The energy source powering these geysers remains debated. Seasonal heating from the distant sun might create subsurface nitrogen reservoirs that explosively vent. Residual tidal heating from Triton's ongoing orbital evolution could provide heat, or radioactive decay in Triton's rocky core might generate enough warmth to drive these eruptions. Triton's fate is sealed. Tidal interactions cause its orbit to gradually decay. In approximately 3.6 billion years, Triton will pass within Neptune's Roche limit, the distance where tidal forces overcome the moon's self-gravity. At that point, Triton will either collide with Neptune's atmosphere in a spectacular impact or break apart, forming a new ring system potentially rivaling Saturn's magnificent rings. Future astronomers, if they exist, will witness Neptune adorned with brilliant rings composed of Triton's scattered remains. Our knowledge of Neptune comes almost entirely from a single spacecraft encounter lasting just hours. On August 25th, 1989, Voyager 2 made its closest approach to Neptune, culminating the spacecraft's grand tour of the outer solar system. The flyby was technically challenging. Neptune's extreme distance meant light levels were 400 times dimmer than Earth experiences. Voyager's cameras required long exposures, risking blur from the spacecraft's motion. Engineers developed sophisticated image processing techniques to compensate, allowing Voyager to capture stunning images of this distant world. Voyager 2 revealed Neptune's dynamic atmosphere, discovered the Great Dark Spot, measured the planet's rapid rotation and powerful winds, detected separate cloud decks that emerged and dissolved within hours, and found that giant storms circled the entire planet in 16 to 18 hours. The spacecraft flew past Triton, discovered its geysers, and measured its frigid surface temperature. Voyager detected Neptune's rings, confirmed their arc structures, and measured the planet's unusual magnetic field. Then Voyager 2 departed, heading into interstellar space. No spacecraft has visited Neptune since. Everything we've learned about Neptune in the past 36 years comes from Earth-based telescopes and space observatories like Hubble and now James Webb. These distant observations have revealed much. The atmospheric temperature changes, the reversing storms, the fading ring arcs, the auroral conformation. But they can't answer Neptune's deepest questions. We need answers that only a dedicated Neptune mission can provide. Why does Neptune's thermosphere burn at 750 Kelvin when it should be frozen? The planet sits 30 times farther from the Sun than Earth. Ultraviolet radiation can't explain temperatures reaching 477 degrees Celsius in the upper atmosphere. Some scientists suggest atmospheric interaction with ions in Neptune's magnetic field generates this heat. Others propose gravity waves from the interior dissipate energy as they reach higher altitudes. But we're essentially guessing. Without direct measurements from an orbiter equipped with specialized instruments, we're trying to solve a puzzle with most pieces missing. Neptune's internal heat generation poses equally baffling questions. The planet radiates approximately 3 times more energy than it receives from the Sun. This internal heat drives Neptune's violent weather despite receiving only 1,000th the solar energy Earth enjoys. Temperatures at Neptune's core reach approximately 5,400 Kelvin, hot enough to vaporize rock. But what generates this heat billions of years after the planet's formation? Gravitational contraction? Radioactive decay? Some exotic process we haven't imagined? Jupiter and Saturn generate internal heat through gravitational compression as they slowly contract. Does Neptune employ the same mechanism, or does something else occur within its mysterious interior? The formation of Neptune itself remains contentious. Traditional planetary formation models struggle with ice giants. These models work reasonably well for terrestrial planets and gas giants. But Neptune and Uranus occupy an uncomfortable middle ground. Core accretion theory suggests planets form when solid material gradually accumulates, eventually capturing surrounding gas if the core grows massive enough quickly enough. The problem? Neptune formed in a region where material was sparse and orbital periods were long. Calculations indicate Neptune should have taken longer to form than the solar nebula existed. Either Neptune formed much closer to the Sun and migrated outward, disrupting the entire early solar system in the process, or our formation models need fundamental revision. Recent discoveries make this ice giant problem more urgent. Exoplanet surveys reveal that Neptune-mass planets are among the most common types of worlds in the galaxy. Understanding how Neptune formed isn't just about our solar system anymore. It's about comprehending planetary system evolution throughout the universe. If we can't explain Neptune's existence, we can't fully understand the thousands of similar worlds astronomers discover around other stars. December 2025 brought Neptune's most startling revelation yet. New hybrid modeling suggests Neptune might not be the icy world we've imagined for decades. The classification ice giant implies a planet dominated by water, methane, and ammonia ices surrounding a small rocky core. But recent analysis indicates Neptune could just as easily be rock-dominated, with rock-to-water mass ratios potentially ranging from 0.20 to 1.78. This isn't a minor refinement. This fundamentally challenges what Neptune actually is. The uncertainty stems from our observational limitations. We've never sent a probe into Neptune's interior. Everything we know comes from gravitational measurements, magnetic field observations, and theoretical modeling. Those observations can support multiple internal configurations. Neptune might contain a relatively small rocky core surrounded by thick layers of exotic ices, or it might possess a massive rocky interior extending halfway to the surface, with only thin ice layers above. Both scenarios match available data. If Neptune is more rock than ice, planetary formation theories face major revision. Rock-dominated Neptune would require different formation conditions, different migration histories, different evolutionary pathways than ice-dominated Neptune. It would mean astronomers have fundamentally misunderstood one of our solar system's major planets for the entire history of modern astronomy. The implications extend to every Neptune-mass exoplanet discovered. Are they ice giants, rock giants, or something between? Computer simulations from recent years suggest Neptune's interior might be even stranger than previously imagined. Models indicate that under the extreme temperatures and pressures inside Neptune, mixtures of water, methane, and ammonia would naturally separate into distinct immiscible layers, like oil and water refusing to mix. Hydrogen would be squeezed out of methane and ammonia molecules that dominate the deep interior, creating a layered structure resembling a cosmic cocktail with components that refuse to blend. This stratification could explain Neptune's bizarre magnetic field. Earth's magnetic field originates from convection in a liquid iron core, a relatively simple dynamo. Neptune's field doesn't work that way. The dramatic tilt and offset suggests the field originates not from a core dynamo, but from thin shells of conducting material in the upper mantle. If Neptune's interior is stratified into immiscible layers, convection would occur differently, generating magnetic fields through mechanisms unlike anything seen on Earth, Jupiter, or Saturn. Neptune and Uranus might represent an entirely different category of magnetic world. Researchers have even identified a candidate molecule that might explain these unusual fields. Aquodium, an exotic substance that cannot form under Earth conditions, might exist within Neptune's high-pressure interior. This molecule could create the conducting layers that generate Neptune's offset, tilted magnetic field. But proving aquodium exists requires direct sampling or detailed spectroscopic analysis from a dedicated mission. From Earth, we're simply too far away to confirm such exotic chemistry. The mystery extends to Neptune's atmosphere. Between 2003 and 2018, globally average temperatures in Neptune's stratosphere dropped by roughly 8 degrees Celsius. This cooling was completely unexpected. Neptune experiences seasons like Earth: summer, winter, spring, and fall. But each Neptunian season lasts over 40 Earth years because Neptune requires 165 years to complete one orbit. During the observation period, Neptune's southern hemisphere was experiencing early summer. Temperatures should have been gradually warming, not cooling dramatically. Then everything reversed. Observations from 2018 to 2020 showed Neptune's south pole warming by roughly 11 degrees Celsius, completely reversing the previous cooling trend. Such rapid polar warming had never been observed on Neptune before. The cause remains unknown. Scientists have proposed several theories. Changes in atmospheric chemistry might alter how effectively the upper atmosphere radiates heat into space. Random weather pattern variability could drive temperature fluctuations. Neptune's atmosphere might respond to the 11-year solar activity cycle, though this seems unlikely, given that Neptune receives only 0.1% of the sunlight Earth enjoys. The solar connection intrigues researchers specifically because it seems impossible. How could a world so distant respond to solar variations, yet correlations appear in the data? When solar activity increases, Neptune's atmosphere seems to warm. When solar activity declines, cooling follows. The mechanism remains mysterious. Perhaps solar wind variations affect Neptune's magnetosphere, which influences upper atmospheric heating. Perhaps cosmic ray flux modulated by solar activity affects cloud formation, altering Neptune's energy balance. Or perhaps we're seeing coincidental correlations in limited data. These temperature mysteries connect to Neptune's storm behavior. Hubble observations revealed something unprecedented in 2018. A massive dark vortex appeared in Neptune's northern hemisphere, an anticyclonic storm similar to Jupiter's Great Red Spot. Over the following year, this storm drifted southward toward the equator. Atmospheric models predicted the vortex would dissipate once it reached equatorial latitudes, torn apart by wind shear and lacking the Coriolis forces that sustain such storms at higher latitudes. But the storm didn't die. In August 2020, the vortex abruptly changed direction, doubling back northward. This represented the first time scientists had observed a Neptunian storm reverse course. Hubble also spotted a smaller dark spot that temporarily appeared near the larger vortex. This smaller feature might have been a piece of the giant storm that broke off, drifted independently, then disappeared. Computer simulations had predicted such fragmentation, but nobody had ever witnessed it actually happening. Dark spots present another Neptune enigma. These massive storms appear preceded by increased cloud activity 2 to 3 years before the vortex becomes visible. The storms exist for only a few years before disappearing. The Great Dark Spot Voyager, two discovered in 1989, had completely vanished by the time Hubble observed Neptune in 1994. New dark spots appear and disappear on irregular schedules. Their formation mechanisms, energy sources, and destruction processes remain poorly understood. The disappearance mechanism might involve companion clouds. High-altitude methane ice clouds often form above dark vortices. These bright companion clouds make the dark spots visible by providing contrast. Some researchers suggest these companion clouds eventually reach the storm's center, blocking the blue wavelengths astronomers use to track the vortex. The storm might still exist, just invisible beneath its cloud cover. Or the companion clouds might somehow disrupt the vortex itself, causing genuine dissipation. Neptune's ring system adds yet another layer of mystery. The Adam's ring contains 5 distinct arcs rather than forming a continuous band. These arcs, named Liberté, Égalité 1, Égalité 2, Fraternité, and Courage, occupy a narrow range of orbital longitudes and have remained remarkably stable since their discovery in 1984. This stability shouldn't exist. Differential orbital motion should cause ring arcs to spread uniformly around Neptune within just a few months. Material in slightly lower orbits moves faster than material in higher orbits, creating shearing forces that should distribute particles evenly. Yet Neptune's ring arcs persist for decades. The leading arcs, Courage and Liberté, have faded recently, but the trailing arcs, Fraternité and Égalité, remain stable and persistent. The stability probably relates to resonant interactions between the Adam's ring and Galatea, Neptune's inner shepherd moon. Galatea's gravity might create zones where ring particles accumulate, maintaining the arc structure against differential shear. But the detailed physics remains unclear, and the recent fading of some arcs while others persist only deepens the puzzle. Neptune's rings contain extremely dark material, likely organic compounds processed by radiation, similar to materials in Uranus's rings. The proportion of dust ranges between 20% and 70%, unusually high compared to Saturn's primarily icy rings. This dust gives Neptune's rings very low optical depth, making them difficult to observe and study from Earth. Even the brightest sections of the Adam's ring reflect less than 0.1% of incident sunlight. All these mysteries, the bizarre magnetic field, the impossible ring arcs, the reversing storms, the unexplained temperature variations, the uncertain interior composition, share a common theme. We're trying to understand Neptune from 4 billion kilometers away, using instruments designed for other purposes. Hubble wasn't built specifically for Neptune. James Webb observes primarily in infrared wavelengths optimized for distant galaxies, not planetary atmospheres. Ground-based telescopes peer through Earth's turbulent atmosphere, blurring fine details. What we need is a dedicated Neptune mission, a spacecraft designed specifically to answer Neptune's deepest questions, an orbiter that could spend years studying the planet's atmosphere tracking storms through complete seasonal cycles, mapping temperature variations across latitudes and altitudes, measuring atmospheric composition and dynamics with dedicated instruments, probes that could descend into Neptune's atmosphere, directly sampling composition, pressure, and temperature profiles, penetrators that could study Neptune's interior structure, magnetic field generation mechanisms, and internal heat sources. Multiple mission proposals exist. NASA's Ice Giants Predecadal Survey Mission Study examined potential Neptune orbiter concepts. The European Space Agency has considered Neptune missions as part of their long-term planning. Chinese Space Agency documents mention outer solar system exploration. Independent academic groups have designed mission architectures, calculated trajectories, and identified key science objectives. But as of 2026, no Neptune mission has received funding or approval. The challenges are formidable. Neptune lies 30 times farther from the Sun than Earth. Solar panels become nearly useless at such distances, requiring nuclear power systems. Travel time exceeds 12 years, even with gravitational assists. Communications suffer from 40-minute light travel delays. Mission costs reach billions of dollars. Competing priorities for Mars, Europa, and near-Earth missions consume available budgets. Yet one critical factor works in Neptune's favor. Triton, Neptune's largest moon, represents one of the most compelling science targets in the outer solar system. Triton orbits Neptune retrograde, revolving opposite to the planet's rotation. This backward motion marks Triton as a captured object, a Kuiper Belt dwarf planet that Neptune's gravity seized billions of years ago. That capture event would have been catastrophic. Gravitational interactions scattered or destroyed any pre-existing Neptunian satellites. Triton's orbit circularized over millions of years through tidal heating, melting and reshaping its interior. The moon we see today bears the scars of this violent history. Voyager 2 found Triton's surface, temperatures reaching negative 391 degrees Fahrenheit, one of the coldest objects ever measured in the solar system. Yet Triton displays remarkable geological activity. Active geysers erupt through its icy crust, driven by sublimating nitrogen ice heated by faint sunlight. These geysers make Triton one of only a few geologically active moons in our solar system. The combination of extreme cold and active geology creates a unique environment. Triton's surface shows evidence of past liquid water, cryovolcanism, and ongoing resurfacing. Its thin nitrogen atmosphere, constantly renewed by sublimation, creates seasonal changes despite the moon's incredible distance from the Sun. Tidal interactions cause Triton's orbit to gradually decay. The moon spirals closer to Neptune by about 4 centimeters per year. In 3.6 billion years, Triton will pass within Neptune's Roche limit, the distance where tidal forces exceed the moon's structural strength. The result will be either collision with Neptune's atmosphere or Triton's breakup, forming a massive ring system potentially more spectacular than Saturn's. A mission to Neptune becomes a mission to Triton by default. Any spacecraft orbiting Neptune could study Triton extensively through repeated flybys. The moon's retrograde orbit simplifies trajectory planning. Its geological activity offers insights into cryovolcanism, tidal heating, and atmospheric dynamics at extreme temperatures. Triton might harbor a subsurface ocean beneath its icy shell. Tidal heating from orbital decay could maintain liquid water layers similar to those suspected beneath Jupiter's moon Europa or Saturn's moon Enceladus. If such an ocean exists, it could potentially support microbial life, making Triton an astrobiology target comparable to the more famous ocean worlds. This dual science return, Neptune itself plus Triton, strengthens mission proposals considerably. You're not just studying one enigmatic ice giant. You're studying a captured Kuiper Belt object, an active cryogenic world, and potentially an ocean moon. 3 major science objectives in one mission architecture. The Voyager 2 flyby demonstrated what's possible with dedicated instruments. On August 25, 1989, Voyager 2 made its closest approach to Neptune, culminating the grand tour of the solar system's 4 giant planets. The encounter was technically challenging due to Neptune's extreme distance and resulting low light levels. Voyager 2's cameras captured images of Neptune's dynamic atmosphere, despite receiving only 3% of the sunlight available at Jupiter. The spacecraft discovered separate cloud decks, cloud systems emerging and dissolving within hours, and giant storms circling the planet within 16 to 18 hours in the upper layers. The mission revealed Neptune's winds, the strongest sustained winds in the solar system, reaching 2,100 kilometers per hour, 3 times stronger than Jupiter's, 9 times stronger than Earth's most powerful hurricanes. This despite Neptune receiving so little solar energy. Voyager 2 discovered the Great Dark Spot, an anticyclonic storm comparable to Jupiter's Great Red Spot. The spacecraft observed Neptune's ring system in detail for the first time, revealing the unexpected ring arcs. It detected Neptune's bizarre magnetic field and measured the planet's internal heat output. The Triton flyby provided equally stunning results. Voyager 2 captured images of the moon's cantaloupe terrain, cryovolcanic features, and active nitrogen geysers. It measured surface composition, atmospheric properties, and geological activity that shouldn't exist on such a cold world. All this from a single flyby, lasting just hours. Imagine what an orbiter could accomplish across years of dedicated observations. Modern mission concepts build on Voyager's foundation while incorporating technologies unavailable in the 1970s. Advanced cameras and spectrometers could map Neptune's atmosphere in wavelengths from ultraviolet through infrared, tracking storms through complete seasonal cycles, measuring atmospheric composition and dynamics with unprecedented precision. Dedicated magnetometers could map Neptune's magnetic field structure in 3 dimensions, determining how the field is generated and why it exhibits such extreme tilt and offset. Plasma instruments could study the interaction between Neptune's magnetosphere and the solar wind, measuring particle populations and energy flows. Atmospheric probes could descend into Neptune's clouds, directly sampling composition, pressure, and temperature profiles at different altitudes and latitudes. They could measure wind speeds at various depths, test predictions about atmospheric chemistry, and search for the transition zones where hydrogen and methane separate into layers. Radar instruments could peer through Neptune's clouds, studying deeper atmospheric layers and potentially even probing the planet's interior structure. Penetrating radar has revolutionized our understanding of Mars, Titan, and Venus. Similar technology could finally answer questions about Neptune's internal composition. Triton would receive comparable attention. High-resolution imaging could map the Moon's entire surface at scales revealing geological processes in detail. Thermal mapping could identify active regions where subsurface heat reaches the surface. Spectroscopic observations could determine surface composition and search for signs of subsurface water. A Triton lander represents a more ambitious but scientifically compelling option. Landing on Triton would be technically easier than landing on Europa or Enceladus due to lower gravity and the absence of intense radiation. A lander could study surface composition directly, measure seismic activity, analyze atmospheric properties, and potentially even detect subsurface ocean signatures through magnetic induction measurements. Several specific mission proposals have progressed beyond initial concepts. NASA's ice giants. Pre-decadal survey examined Neptune orbiter architectures in detail. One concept featured a main orbiter studying Neptune, plus a Triton lander deployed after Neptune orbit insertion. Launch windows occur approximately every 13 years, with the next optimal opportunity in the early 2030s. The European Space Agency has considered Neptune missions as part of their Voyager 2050 long-term planning framework. ESA concepts emphasize international collaboration, potentially partnering with NASA or other space agencies to share costs and technical expertise. European contributions might include specific instruments, atmospheric probes, or mission components leveraging ESA's experience with Rosetta, Huygens, and other planetary missions. Chinese Space Agency documents mention outer solar system exploration as part of long-term objectives. China's successful Mars and lunar missions demonstrate growing technical capabilities. A Neptune mission could represent a flagship achievement, showcasing Chinese space technology while contributing valuable science data to the international community. Independent academic groups continue designing mission concepts and advocating for ice giant exploration. These studies identify key science questions, design instrument packages, calculate trajectories, and estimate costs. While lacking official funding, academic mission designs often influence later formal proposals by demonstrating technical feasibility and scientific value. The technical challenges remain formidable, but not insurmountable. Solar panels become nearly useless at Neptune's distance, requiring nuclear power systems. NASA's multi-mission radioisotope. Thermoelectric generators provide reliable power regardless of distance from the Sun. These systems powered Voyager 2, Cassini, Curiosity, and Perseverance successfully. Travel time exceeds 12 years, even with gravitational assists from Venus, Earth, and Jupiter. This requires spacecraft systems robust enough to survive decades in the harsh space environment. Radiation exposure, micrometeorite impacts, thermal cycling, and component aging all threaten long-duration missions. Communications suffer from 40-minute light travel delays at Neptune's distance. Commands sent from Earth take 40 minutes to reach the spacecraft. Responses take another 40 minutes to return. This precludes real-time control during critical mission phases like orbit insertion or probe deployment. Spacecraft must execute these maneuvers autonomously, using pre-programmed sequences. The distance also reduces data transmission rates dramatically. Radio signals spread out over vast distances, arriving at Earth extremely weak. Even with large ground antennas and sensitive receivers, data rates at Neptune remain far slower than at Mars or even Saturn. High-resolution images and spectroscopic data must be transmitted gradually over days or weeks. Mission costs reach several $billions. Voyager 2 cost approximately $4 billion in today's currency. Modern missions with more sophisticated instruments, longer operational lifetimes, and additional mission elements like probes or landers would cost considerably more. NASA's proposed Neptune orbiter concepts range from $3 to $5 billion. Competing priorities consume available budgets. Mars Sample Return, Europa Clipper, Dragonfly to Titan, and various near-Earth missions all vie for the same funding. Political realities mean flagship missions require sustained commitment across multiple administrations. Budget uncertainties and changing priorities can derail missions even after approval. Despite these obstacles, the scientific case for Neptune exploration remains compelling. Neptune represents an entire class of planets, ice giants, that appears common throughout our galaxy. Exoplanet surveys reveal Neptune-mass worlds orbiting other stars frequently. Understanding ice giant formation, composition, and evolution informs our understanding of planetary systems generally. The ice giant problem, explaining how Neptune and Uranus formed, remains unsolved. Traditional core accretion models struggle with timing. Planets either grow too slowly to capture substantial nebular gas before it dissipates, ending up as small rocky worlds without hydrogen-helium envelopes, or they grow so rapidly they reach runaway gas accretion and become hydrogen-dominated gas giants like Jupiter. Forming ice giants with substantial fractions of both heavy elements and hydrogen-helium requires precise timing and fine-tuning in models. Recent theories propose Neptune and Uranus formed closer to the Sun, then migrated outward through gravitational interactions with other planets and remaining planetesimals. Testing these formation scenarios requires detailed knowledge of Neptune's interior composition and atmospheric properties. Neptune's extreme weather, despite minimal solar heating, challenges our understanding of atmospheric dynamics. Internal heat drives Neptune's storms and winds, but the mechanisms remain unclear. Studying Neptune's weather through complete seasonal cycles would reveal how internal and external energy sources interact to produce atmospheric phenomena. The bizarre magnetic field requires explanation. Recent computer simulations suggest water, methane, and ammonia separate into immiscible layers under the temperatures and pressures inside Neptune. Hydrogen gets squeezed out of methane and ammonia in the deep interior, creating stratified layers like oil and water. These immiscible layers might explain why Neptune's magnetic field differs so dramatically from Earth's, Jupiter's, and Saturn's. The field might originate from thin conducting shells in the upper mantle rather than deep core convection. This layered interior model has profound implications. If correct, it suggests Neptune's interior structure is far more complex than the simple three-layer model that dominated thinking for decades. It would explain not just the magnetic field, but also observations about Neptune's heat flow, atmospheric composition, and possibly even the diamond rain forming deep inside. Testing this model requires detailed measurements impossible from Earth. We need to map Neptune's gravitational field precisely, revealing mass distribution inside the planet. We need to measure how Neptune's magnetic field varies with location and time, constraining where and how the field is generated. We need atmospheric composition measurements at different depths, testing predictions about how materials separate under extreme conditions. Triton adds urgency to mission planning. The Moon's gradual orbital decay means its geological activity might not persist indefinitely. Studying Triton now captures a unique window when the Moon remains geologically active, maintains a thin atmosphere, and displays ongoing resurfacing. Delaying decades might mean missing Triton's active phase. The Moon's potential subsurface ocean represents another time-sensitive target. If tidal heating from orbital decay maintains liquid water beneath Triton's ice shell, that ocean might support microbial life. Studying Triton joins the search for life beyond Earth, alongside Europa, Enceladus, and Titan. These ocean worlds represent our best near-term opportunities to discover extraterrestrial biology. So Neptune waits, 4 billion kilometers away, wrapped in mysteries we've barely begun to unravel. Its bizarre magnetic field wobbles through space. Diamond rain falls through its depths. Storms reverse course for reasons unknown. Ring arcs persist against all expectations. And nearby, Triton erupts with geysers while slowly spiraling toward eventual destruction. Every mystery points toward the same conclusion. We need to go back. The scientific case grows stronger each year. NASA's Planetary Science Decadal Survey identified an ice giant mission as a priority, recognizing that Neptune and Uranus represent a major gap in our exploration of the solar system. We've sent multiple missions to Mars, several to Jupiter and Saturn, yet we've visited the ice giants only once, briefly, decades ago. That imbalance reflects outdated priorities from an era when we didn't understand how common Neptune-mass planets are throughout the galaxy. Exoplanet discoveries changed everything. Telescopes like Kepler revealed that Neptune-sized worlds are among the most abundant planets orbiting other stars. They're more common than Jupiter-sized gas giants, more common than Earth-sized terrestrial planets. Understanding how these intermediate mass planets form, evolve, and develop atmospheres suddenly became crucial for interpreting observations of thousands of exoplanets. Neptune stopped being just another solar system member and became the template for understanding the galaxy's most typical large planets. Several mission concepts have been proposed. The Trident mission would conduct a single flyby of Neptune and Triton, similar to Voyager 2, but with modern instruments. It would map Triton's surface at high resolution, measure atmospheric composition on both bodies, and study Neptune's magnetic field during the encounter. A flyby mission could be built relatively inexpensively and launched within a decade, providing quick returns on scientific investment. But flyby missions have limitations. Voyager 2 taught us that brief encounters reveal mysteries without answering them. The Great Dark Spot appeared in Voyager images, then vanished by the time Hubble looked again. Was it dissipating during Voyager's approach? Did it form shortly before the flyby? We'll never know because we only had those few hours of observation. Understanding Neptune's dynamic atmosphere requires watching storms evolve over weeks and months, tracking how they form, drift, and disappear. Orbiter missions offer that extended observation time. A Neptune orbiter could spend years studying the planet and its moons, watching complete seasonal cycles, tracking magnetic field variations, monitoring atmospheric changes. It could observe Triton repeatedly from different angles and distances, mapping the entire surface at high resolution while studying how geysers vary with orbital position and seasonal timing. An orbiter transforms brief glimpses into comprehensive understanding. The technical challenges are formidable. Neptune orbits 30 times farther from the Sun than Earth, where sunlight is 900 times dimmer. Solar panels that work perfectly near Earth generate almost no power at Neptune. Nuclear power becomes necessary. Radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity, provide the only viable power source. But these systems are expensive, require rare plutonium-238, and generate limited power compared to solar panels. Communication presents another challenge. Radio signals from Neptune take over 4 hours to reach Earth, traveling at light speed across 4 billion kilometers. That 8-hour round-trip delay makes real-time control impossible. Spacecraft must operate autonomously, making decisions without waiting for instructions from mission control. They need sophisticated onboard systems capable of recognizing and responding to problems, adjusting observations based on what they find, managing power and data storage independently. Getting to Neptune takes time. Even with gravity assists from Jupiter, the journey requires 12 to 14 years. Engineers must design systems that remain functional after more than a decade in space, exposed to radiation and micrometeorite impacts. Every component must be redundant, every system robust enough to survive the long voyage. The mission profile demands patience, committing to science returns that won't arrive until the 2040s at the earliest. Cost compounds these challenges. Outer planet missions rank among the most expensive robotic spacecraft NASA builds. The Cassini mission to Saturn cost over $3 billion. A Neptune orbiter would likely cost similar amounts, competing with other scientific priorities for limited budget resources. Planetary scientists must make difficult choices, balancing the transformative science from Neptune against equally compelling targets elsewhere in the solar system. Yet the scientific payoff justifies the investment. Neptune's mysteries touch fundamental questions about planetary formation, atmospheric dynamics, magnetic field generation, and the potential for life in ocean worlds. Solving these mysteries advances our understanding not just of one distant planet, but of planetary systems throughout the universe. Consider what we'd learn about planetary interiors. Precise measurements of Neptune's gravitational field would reveal how mass is distributed inside the planet, testing models of layered versus uniform composition. Does Neptune have distinct shells of different materials? Or does its interior mix gradually from the rocky core through ice-rich mantles to the gaseous atmosphere? Gravitational data combined with magnetic field measurements would constrain interior structure, revealing whether the immiscible layer model correctly explains the bizarre magnetic field. Atmospheric studies would revolutionize our understanding of weather on ice giants. Observing Neptune through complete seasonal cycles would show how atmospheric dynamics respond to changing solar heating, internal heat flow, and seasonal variations. Why does Neptune's atmosphere cool unexpectedly? Why do storms reverse course? How do winds reach supersonic speeds with minimal solar input? Long-term observations would answer these questions, revealing the fundamental physics governing ice giant atmospheres throughout the galaxy. The magnetic field deserves dedicated study. Neptune's field wobbles dramatically as the planet rotates because the field center is offset from the rotation axis. Mapping how this field varies with position and time would reveal where currents flow in Neptune's interior, testing theories about thin shell dynamos versus core convection. Understanding Neptune's magnetic field would illuminate a regime of planetary magnetism unlike anything seen elsewhere, with implications for how magnetic fields are generated in intermediate mass planets around other stars. Triton demands exploration. The Moon's active geology, thin atmosphere, and potential subsurface ocean make it one of the solar system's most intriguing bodies. Is there liquid water beneath Triton's ice shell? Does that ocean connect to the surface through geological activity? Could it harbor life, protected from space radiation by kilometers of ice while warmed by tidal heating? An orbiter could study Triton repeatedly, mapping surface composition, measuring ice shell thickness through radar sounding, and monitoring geysers to understand what drives them. The ring system needs investigation. Why do some arcs persist while others fade? How do shepherd moons maintain arc stability despite differential orbital motion that should disperse them? What processes create the dark ring material? Close observations would reveal ring particle composition, size distribution, and dynamics, testing theories about how rings evolve and interact with nearby moons. Other moons deserve attention. Neptune has 14 known moons, most discovered recently and barely studied. Proteus, Neptune's second largest moon, shows a heavily cratered surface, suggesting ancient geology. Nereid follows an extremely elongated orbit, possibly indicating capture from the Kuiper belt. Smaller, irregular moons might be captured asteroids or fragments from ancient collisions. Understanding Neptune's moon system would reveal the complex gravitational dynamics and collisional history of the outer solar system. Mission planning is underway. NASA's Jet Propulsion Laboratory has studied various Neptune mission architectures, evaluating different trajectories, payloads, and scientific objectives. European and Chinese space agencies have proposed their own ice giant missions. International collaboration might enable the mission too expensive for any single agency, combining resources and expertise to achieve shared scientific goals. Technology continues advancing. Ion propulsion systems could reduce travel time. Advanced power systems might generate more electricity from radioisotope sources. Improved autonomous navigation would allow spacecraft to adjust trajectories without Earth-based control. Better radiation-hardened electronics would survive the journey more reliably. Each year brings incremental improvements that make ambitious missions more feasible. Public interest supports exploration. Neptune captures imagination despite its distance. People want to know what secrets hide in that distant blue world. What forces drive its impossible storms? What mysteries lurk beneath its clouds? That curiosity translates into support for space exploration, encouraging funding agencies to prioritize missions that address fundamental questions about our solar system. The window is closing. Triton's orbital decay means the moon's geological activity might not persist indefinitely. Future generations might find a geologically dead world, its geysers extinct, its atmosphere collapsed. Studying Triton now captures a unique moment in solar system history when this captured Kuiper Belt object remains active enough to reveal its secrets. Neptune's formation history connects to exoplanet science. Understanding how Neptune formed and migrated inward helps interpret observations of Neptune-mass exoplanets orbiting other stars. Did those planets form in place or migrate? Do they have similar compositions and interior structures? Do they generate magnetic fields like Neptune's or follow different patterns? Answering these questions requires understanding our own ice giant thoroughly. The broader context matters. Neptune represents a class of planets that dominates galactic demographics. Every insight we gain about Neptune informs our understanding of thousands of exoplanets we'll never visit. Every mystery we solve about Neptune's weather, interior, or magnetic field helps interpret observations of distant worlds orbiting alien suns. Neptune stopped being just our solar system's eighth planet and became a key to understanding planetary diversity throughout the universe. Future telescopes will discover more Neptune-like exoplanets. The James Webb Space Telescope already studies exoplanet atmospheres, detecting molecules and measuring temperatures on worlds dozens of light years away. Future missions will push these capabilities further, characterizing atmospheres in increasing detail. But interpreting those observations requires understanding how ice giant atmospheres behave. What drives their weather? What chemical processes occur under different conditions? Neptune provides the ground truth for interpreting distant observations, so the case is clear. Neptune demands exploration not just for its own sake, but for what it teaches us about planetary systems everywhere. The mysteries accumulating since Voyager 2's brief encounter call for resolution. The bizarre magnetic field, the diamond rain, the reversing storms, the persistent ring arcs, the erupting moon. Each mystery represents a question about fundamental physics that extends far beyond one distant planet. The journey won't be quick or easy. Engineers face formidable challenges, designing systems that survive the decade-long voyage and operate reliably in Neptune's harsh environment. Scientists must prioritize limited observations, choosing which questions to address first among dozens of compelling mysteries. Budget planners must justify the expense against competing priorities. But the scientific returns justify every challenge. Neptune reveals planetary processes operating in regimes we've barely explored. Its weather runs on internal heat rather than solar input. Its magnetic field emerges from thin conducting shells rather than deep core convection. Its interior might separate into immiscible layers like oil and water. Its largest moon erupts with nitrogen geysers, despite being one of the coldest objects in the solar system. Every aspect of the Neptunian system challenges our understanding and expands our knowledge of what's possible. That's why we need to go back. Not just to satisfy curiosity, though Neptune certainly deserves our curiosity. Not just to complete the catalogue of solar system planets, though that remains unfinished business. We need to return to Neptune because understanding this distant world illuminates planetary processes throughout the universe. Because the mysteries we uncovered decades ago still await resolution. Because Neptune's secrets might reveal how planets form, how atmospheres evolve, how magnetic fields are generated, and whether life can exist in ocean worlds far from the sun. The universe contains billions of Neptune-like planets. We've studied exactly one of them for exactly one day, 37 years ago. Everything we've learned since then came from telescopes pointed across 4 billion kilometers of space, squinting to see details on a distant blue disk. That's not enough. The questions we've accumulated, the mysteries we've discovered, the fundamental physics we've glimpsed, all demand closer examination. Neptune calls us back across the solar system's edge, promising revelations about planetary science that ripple throughout our understanding of the cosmos. The journey is long, the challenges substantial, the wait frustrating, but the destination holds answers to questions we're only beginning to formulate, mysteries we've barely started to recognize, and insights that will reshape how we understand not just Neptune, but thousands of worlds throughout the galaxy that share its nature. Looking up at the night sky, you can't see Neptune without a telescope. It's too distant, too faint, lost in the cosmic darkness beyond Saturn. Most people live their entire lives without thinking about it. Just another planet in textbooks, another blue circle in diagrams, another entry in the catalogue of worlds orbiting our sun. But Neptune isn't just another planet. It's a warning written across 4 billion kilometers of space that the universe refuses to behave according to our comfortable assumptions. Every certainty we held about Neptune has crumbled under scrutiny. The iconic deep blue color, artificially enhanced. The simple ice giant composition, possibly more rock than ice. The stable atmospheric temperatures, wildly variable for reasons unknown. The predictable storm behavior, storms that reverse course and defy every model. Even the planet's discovery, astronomy's greatest mathematical triumph, succeeded despite calculations being fundamentally wrong about Neptune's mass. We've been wrong about almost everything. This isn't a failure of science. It's a revelation about the nature of reality itself. The universe operates according to principles far stranger than we imagined when we first pointed telescopes toward that distant blue speck. Neptune's mysteries aren't bugs in our understanding. They're features of a cosmos that delights in exceeding our expectations. Diamond rain falls through superionic ice. Magnetic fields wobble from offset centers. Storms rage at supersonic speeds, powered by internal furnaces. Ring arcs persist where orbital mechanics says they should dissipate. A moon erupts with nitrogen geysers at temperatures that should freeze all activity solid. Each discovery reveals physics operating in regimes we've barely explored, under conditions we can't recreate in laboratories, at scales that challenge our ability to observe or measure. And we've observed all this from 4 billion kilometers away, mostly based on a single spacecraft encounter that lasted less than a day, 37 years ago. Imagine what we've missed. What processes occur during Neptune's 40-year seasons that we've never witnessed? What transient phenomena appear and vanish between our infrequent observations? What subtle variations in magnetic field structure, atmospheric chemistry, or ring dynamics escape detection because we're watching from so impossibly far away? The exoplanet revolution transformed Neptune from solar system curiosity to galactic archetype. Telescopes discovered that Neptune-mass planets are among the most common worlds orbiting other stars. They're everywhere, more abundant than gas giants like Jupiter, more prevalent than rocky worlds like Earth. Understanding ice giants suddenly became crucial for interpreting observations of thousands of exoplanets we'll never visit. Every mystery about Neptune is really a question about planetary processes throughout the galaxy. How do intermediate mass planets form in protoplanetary disks? What determines whether they become ice-dominated or rock-dominated? Why do some develop bizarre, offset magnetic fields while others generate Earth-like dipoles? How do their atmospheres respond to different levels of stellar heating? What drives their weather when internal heat dominates over external energy input? Neptune holds answers to all these questions, but only if we go back. The technical challenges are real. Nuclear power requirements, decade-long travel times, autonomous operations across light-hour communication delays, multi-billion-dollar price tags competing with other scientific priorities. These aren't trivial obstacles. They're why Neptune remains the least explored planet in our solar system, despite being discovered in 1846. Yet those challenges grow less insurmountable each year. Power systems improve. Propulsion becomes more efficient. Autonomous navigation grows more sophisticated. International collaboration enables missions too expensive for single agencies. The technology that seemed impossible when Voyager 2 launched in 1977 is routine today. The technology that seems daunting now will be commonplace when a Neptune orbiter finally launches. The real question isn't whether we can go back. It's whether we choose to. Whether we decide that understanding ice giants matters enough to commit resources and time to the endeavor. Whether Neptune's mysteries deserve the same attention we've devoted to Mars, Jupiter, and Saturn. Triton adds urgency. The moon spirals inward, gradually losing orbital energy to tidal friction. Its geological activity might not persist indefinitely. The geysers erupting today could fall silent as tidal heating diminishes. The thin atmosphere might collapse as the moon's activity wanes. We're witnessing Triton during a geologically active phase that might not last. Future generations could find a dead world, its secrets frozen beneath ancient ice. More immediately, the scientific questions accumulate faster than we can answer them from Earth. Neptune's atmospheric temperature dropped 8 degrees over 15 years. Then the South Pole warmed 11 degrees in just 2 years. Why? Some ring arcs faded while others persisted. Why? A storm reversed course against all predictions. Why? Each observation generates more questions than answers because we're trying to understand a dynamic, evolving world through snapshots separated by months or years. The case for returning to Neptune isn't about satisfying curiosity. Though Neptune certainly deserves our curiosity, it's not about completing the catalogue of solar system exploration, though that remains unfinished business. We need to go back because Neptune illuminates planetary processes operating throughout the universe. Because understanding ice giants transforms how we interpret exoplanet observations. Because the mysteries we discovered decades ago still await resolution, and new mysteries appear with every observation. Most fundamentally, we need to return because Neptune challenges everything we thought we knew about how planets work. It's a world that shouldn't be where it is, shouldn't generate the heat it produces, shouldn't drive weather as violent as it displays, shouldn't maintain magnetic fields as bizarre as it possesses. Every aspect of Neptune's existence contradicts comfortable assumptions about planetary physics. That's exactly why it matters. Science advances not by confirming what we already believe, but by discovering phenomena that force us to expand our understanding. Neptune is a masterclass in how the universe exceeds our theories, how nature operates according to principles we haven't yet grasped, how reality resists reduction to simple models. The next mission to Neptune won't just study one distant planet. It will revolutionize our understanding of how planets form, evolve, and behave under conditions far from their parent stars. It will test theories about planetary interiors, atmospheric dynamics, magnetic field generation, and orbital evolution. It will reveal whether Triton's subsurface ocean exists and potentially harbors life. It will answer questions we've carried for 37 years while raising new questions we haven't yet imagined. And somewhere beyond Neptune, in the darkness past Triton's orbit, the Kuiper Belt stretches outward toward interstellar space. Billions of icy objects orbit in that distant realm, leftover building blocks from the solar system's formation, pristine samples of the material that built the planets. Triton came from there, captured billions of years ago when it wandered too close to Neptune's gravity. What other treasures wait in that frozen frontier? A Neptune orbiter could study Kuiper Belt objects during its journey or after completing its primary mission. It could observe these distant worlds up close, revealing their compositions and structures in ways impossible from Earth. It could transform our understanding of the solar system's outer edge while simultaneously revolutionizing ice giant science. The path forward requires vision, commitment, and patience. Engineers must design systems that survive the decade-long voyage. Scientists must prioritize observations among dozens of compelling mysteries. Funding agencies must commit resources despite competing priorities. The public must support exploration that won't return results for 15 or 20 years. But the destination justifies the journey. Neptune represents a class of planets dominating galactic demographics. Every insight gained there illuminates thousands of exoplanets orbiting distant stars. Every mystery solved advances our understanding of planetary processes throughout the universe. Neptune isn't just our solar system's 8th planet. It's a key to comprehending planetary diversity across the cosmos. The universe is vast, ancient, and filled with wonders that exceed our capacity to imagine. Neptune reminds us that even in our own solar system, even among planets we've known for nearly 2 centuries, mysteries persist that challenge our deepest understanding. It reminds us that the cosmos refuses to behave according to our comfortable assumptions, that nature operates according to principles far stranger than we've yet grasped. That's not a limitation of human knowledge. It's an invitation to explore, to question, to push beyond the boundaries of what we think we know. Neptune calls across 4 billion kilometers of space, promising revelations about planetary science that ripple throughout our understanding of the universe. The only question is whether we have the courage to answer. 4 billion kilometers away, diamond rain falls through exotic ices. Magnetic fields wobble through space. Storms reverse course for reasons unknown. Ring arcs persist against all expectations. A moon erupts with geysers while spiraling toward eventual destruction. And beneath it all, Neptune keeps its secrets, waiting for the day we finally return with instruments capable of revealing what it's been hiding all along. That day can't come soon enough. The mysteries won't solve themselves. The questions won't answer themselves. Neptune won't come to us. We have to go back.